Alright, we are going to get started here with the derivative of just some general function a to the x. Now we've already done e to the x, and we know its derivative is also the same thing, just e to the x. Alright, well I wonder if we can use that to just for any base as opposed to just specifically e. So we're going to see if we can swap that out here and carry out a little switch. So the base of any exponential function naturally is e, and this natural base can be used to assign meaning to some general base. Okay, so if I have some function, exponential function, to the base a, it's denoted by a to the x, and we can repeat this. Let me back up here just a moment because that's not entirely correct here. Let's get rid of that. It's e to the natural log of a times x. Okay, so what does that mean in terms of just kind of swapping out? Basically, what we're doing is replacing the base, so that way it is easier to differentiate. Is pretty much what it is. It's just a lot easier to differentiate. So how does that look in terms of a formula? Well, if this is my y and I want y prime, remember what the rule is for e to the x. It is e to the ln of a times x, and then we're going to multiply that by the derivative of the upper function. Okay, well, this upper function right here is this natural log of a times x, so its derivative is just natural log of a. Now, I can go ahead and do a swap out now, and I can replace this entire thing right here with a to the x, because that's how I defined it. So we're going to do a little bit of a switch out here, and that's going to make this a to the x times the natural log of a, and that's going to be my derivative for any general exponential function. Okay, so let's go ahead and fill that in there, and the derivatives of bases other than e, it's going to be a to the x times the natural log of a. Okay, so if it's any garden variety function u that is going to be inside the differentiable part, for, satisfy the chain rule like we've been talking about, it's going to be a to the u times the natural log of a times du over dx, just like we've talked about with this chain rule. Okay, so shouldn't be too much trouble here to differentiate these things, even if you've got a nested function on the inside. So let's take a look at a couple of examples here on how that's going to look. It's just simply going to be the same function times the natural log of the base, and that's all there is to that. Pretty straightforward, nothing too difficult. Okay, here, since we've got a nested function, our derivative is going to be the same thing that we had before. Let me touch that up a little bit, make it look better. Okay, so it's the same function, 2 to the 3x times the natural log of 2 times the derivative of the so-called inner function, which is this 3x. Well, it's just 3, really. Alright, now you got to be careful with this because you've got to make sure that you don't combine things in the wrong spot. Okay, so if you combine things in the wrong spot, that could get you into a little bit of trouble here, which would be very unfortunate. All you can really do is keep your terms as separate as possible. So what do we mean by that? Well, you can't combine anything with this base of 2 because it's just not the way it works. So the only thing that you can really do to make this look a little better is 3 times the natural log of 2 times 2 to the 3x. Just reorder this, and then maybe if you remember your log properties a little bit, if you remember those, you might recall that this guy can go upstairs right there. And we can clean that up just even a little bit more. 3 times the natural log, oopsies, see, I told you to do it and then I didn't do it myself. Let's try that again. So natural log of 2 cubed times 2 to the 3x, and really that's about it, unless you want to just tell me that the natural log of 2 cubed is the same as the natural log of 8. Okay, so not very difficult to follow these rules for derivatives. We've got a good question here. At what point does the graph of the function y is equal to 2 to the t minus 3, does that tangent have a slope of 21? Okay, well, the magic word here is, of course, tangent has a slope, and of course that's going to signal that we're going to need to take a derivative. So let's go ahead and take a look at what that really means here. We need what y prime is, so let's go for it. Y prime, and now I get to apply one of these lovely rules here. I get to apply this one that I just learned about 2 to the t. So let's take a look and see what it's going to lead me to here. Alright, so this first part is going to be 2 to the t times the natural log of 2. Okay, and then of course the minus 3 drops out. So I'm looking for when this particular function, oopsies, sorry about that, folks. I'm looking for when this 2 to the t has a slope of 21. So 21 equals 2 to the t times the natural log of 2. Okay, well, I'm going to go ahead and divide on both sides here by the natural log of 2. So I get 21 over ln 2 is equal to 2 to the t. Alright, and now what I really want to do is I really want to take the natural log of both sides. And when I do that, I'm going to end up with, let's see, the natural log of 21 over ln 2 is equal to t ln 2. Now where did I get that from? Well, that's going to be the power rule. If I take the natural log of 2 to the t, it's going to be the same thing as seeing t times the natural log of 2. So that's where that comes from. Okay, so got to get t all by itself, no big deal. Just divide everything by natural log 2. And let's kind of see where that leads us here. So our t ends up being the natural log of 21 over ln 2 all over ln 2. Ugh, it's pretty hideous. Natural log of 21 over ln 2. Yeah, that's kind of disgusting. Okay, now you can get this out of your calculator, and I'll spoil the surprise for you. It's going to be about 4.921 if you were to reach into your calculator and grab that. So you need to know the point at which this occurs. So we're going to take this and put it back into the original function, the 2 to the t minus 3. And when you do that, the final answer has an x-coordinate of 4.921 and a y-coordinate of 27.927. Okay, kind of disgusting, but not all that bad. As we pick up on this part right here with the derivative of the natural log function, I'm not going to really do the proof right now because I think that's just going to take really quite a bit of a mess. But it's really, truth be told, it's not that bad. If I were to rewrite this as e to the y equals x, just by exponentiating both sides, and I do implicit differentiation, then I'm going to get e to the y dy over dx is equal to 1. Okay? And then what I simply do is divide both sides by e to the y. So dy over dx equals 1 over e to the y. But now, this is the sneaky part. Because I've already defined this to be x, I can now do a little bit of a swap. And this is now equal to 1 over x. So that's just like a really sneaky proof of why the derivative of the natural log function is just 1 over x. Pretty easy to handle. So if we had a nested function u in there, it would be 1 over u times du over dx, or du over dx all over x, u, excuse me, as you prefer. That should be a u down there. Let me change that up just a touch. There we go. Okay, so finding these derivatives is just pretty straightforward and easy. So let's just go ahead and maybe knock out a couple of these examples. The derivative of this one is just 1 over 2x, but then you multiply by the derivative of the inner function, which is just 2, so it reduces to 1 over x. No big deal. Okay, so in b over here, that one is 1 over x squared plus 1. Try that again, make it look better. And then what you do is you have to multiply by the derivative of that inner function, which is just 2x. So it's 2x all over x squared plus 1. Just that easy to come up with. Okay? Not bad. So let's move on to something that's a little bit more involved here, and that of course would entail the product rule. Yikes. So this is actually not too bad. Just play along with me here. We're going to call the red function my first one and the blue one my second one here. So it is first times the derivative of the second plus second times the derivative of the first, which in this case is just 1. So once you cancel out and clean up, it's going to be 1 plus ln x. Pretty straightforward. Not too bad to do. Okay, and now we're going to come over here and try this one. And this one is going to require the chain rule, of course. This is like saying u to the third, where your u is ln of x. Okay, so that's going to be what this boils down to. So 3u squared du dx. Well, what is du over dx? It's just simply 1 over x. So what I really have here is 3 natural logs of x raised to the second power times 1 over x. Okay, so that's just going to simplify into 3 natural log x quantity squared all over x. And that's going to take us pretty much to this last example here in E, where I have natural log of x cubed. Okay, pretty easy to do. So 1 over x cubed times 3x squared. Oh, well that's convenient. So we're going to get a whole bunch of stuff to drop out here, and it's going to end up being 3 over x when it's all said and done. Okay, that's going to hit the pause button for this part, and another video is forthcoming.